Well, actually, my talk will be a little bit different from the other one. There will be very few physics. On the contrary, pictures, letter, and this kind of thing, just to tell you what were my relation with John Bell. And they also allow me to pinpoint some situation in which discussion with John have been useful for me. So this is recollection of a great scientist and a great man. I stress also great man. These are my affiliation. And so let me start. The first thing I will project Bell, and I would like to stress that in my opinion it has been undoubtedly one of the greatest physicists of the 20th century. I consider a big scandal, as many other people do, that he did not get the Nobel Prize, and that I remember that Abdus Salam told me, because I had daily contact with Abdus Salam, because I was the director of the department in which ICTP is located, and he told me various times that John arrived among the last 2 or 3. But, first of all, foundation of quantum mechanics are not so popular. Secondly, John is surely a person who did not do anything of those actions which also for very good physicists are necessary to get the Nobel Prize. This is my opinion, and so this is what happened. Okay, apart from his various fundamental contributions to science, his greatest merit is to have compelled the scientific community to accept something that nobody had not even dared to suspect before his work, that nature is non-locally causal. So I would claim that it is not an illusion, non-locality. Okay, well, I have been one of those lucky persons who became acquainted with him personally, who has exchanged important views with him, who has learned a lot from his deep insight and conceptual lucidity, and last but not least, one whose scientific work has been appreciated by him, and I apologize if some of the sentences that I will show that come from Bell seems to be something which praises me, but it is just made for making clear to you what was the position of John concerning the theory I will discuss. Okay, before proceeding, let me remember that he obtained various important recognitions, the Hugh Medals of the Royal Society, the Dirac Medal of the Institute of Physics, the Heinemann Prize of the American Physical Society, and I want to mention here the honorary degree at Queen's College, Belfast, and in one of these letters that I brought, which are the letter in which I have recently exchanged with Mary Bell, in one of them there is a sentence that she told me that in November there will be an exhibition, and that with great probability there is the possibility of a street of Birmingham being named after John. That is a good news, and I wanted to bring it here in this, on this occasion of celebrating John Bell. Okay, so let me just go very quickly through some data about his career and fundamental contribution to science, both related, but I will start from those who are not related to foundational problems in the standard sense. He was graduated in experimental physics in 1948, and then a second time in mathematics in 1949. He was immediately rather unsatisfied and critical about the orthodox interpretation of quantum mechanics. You remember that he wrote that he had big struggle with some of his teachers about the Copenhagen interpretation. Then he went to Harwell and he joined the AERE, and then he started to work with accelerator design. More or less in this year, he has met Mary Bell. They were married in 1954. Okay, at the beginning he was modeling the path of charged particle in accelerator, and at that time in which there were no efficient computers, it was quite an hard thing, and I have been told by various people, for instance by Linnaeus was working with him, that he had very, very smart ways of circumventing difficult mathematical problems. And in one of his papers you can also find a suggestion of the strong focusing of the beams in an accelerator. So also this is, you remember that there is that tail area in which the particles are strongly focused in order not to lose them. So this is important. Well, in 1951 he worked with Pyers, and he has been the first to prove at Birmingham the CPT theorem, which became known as the Luders-Pauli theorem. And I would like to report here the comment by Veltman. His very first work in the domain of field theory is a very important one and concerns the CPT theorem. It was unfortunate for him that Pauli and Luders had also tackled the subject and simply dominated it. John's article, Time Reversal in Field Theory, was, as I remember from personal discussion, conceived independently. It is, of course, very different and perhaps today more relevant than the rather formal field theory argument of Luders. In his introduction, John acknowledged the paper of Luders and never sought to even suggest that his work has been done independently. Problems relating to time reversal invariance were very fascinating to him, and that interest can be seen as a theme in his scientific career. It really reflected his interest in the very foundation of physics. So the CPT theorem, for sure, he has independently derived it. Okay, now let me go on. He got the PhD in 1956 and moves to CERN in 1960. Then I would like to remember that in 1967 he argued that weak interaction should be described using gauge theories and pointed out the relation between current algebra and gauge invariance. Finally, in 1969 he discovered the Bell-Jacquier-Adler anomaly, something which is a very relevant paper for the development of modern science. So I went through all this. However, quantum theory was his hobby, perhaps his obsession, and it made him famous. He had always been rather worried by the fact that quantum variables do not have a value and by the problem related to quantum measurement. He was also repelled by the complete lack of clarity and incoherence of Bohr complementarity. He was very upset by Bohr papers on complementarity. Okay, in 1952, as he has written, he has read the paper by Bohm, and this has been a revelation for him because he has seen the impossible done, which means that he has seen that what von Neumann had proved was impossible, to have a deterministic completion of quantum mechanics was actually possible, in discovering the fact that the starting point of von Neumann, obviously the theorem is correct, von Neumann was too good a mathematician to make a mistake, but the assumptions are not logically cogent in a sense. And in 1963, it has been published in 1966 for some editorial accidents on leave at Stanford, he proved the logical irrelevance of von Neumann's no-go theorem concerning hidden variable. He identified the contextual nature and comment on the contextual nature of deterministic hidden variable, and he pays a particular attention to the non-locality of Bohm theory. Actually, he told me that after he has seen Bohm, he said, I must do the same with the local theory, but exactly what Bohm did. And then I tried, and since I did not succeed, I got the idea that probably I could prove that it was impossible to do this. Okay. In 1964, precisely 50 years ago, and here we are celebrating this event, during his stay at Brandeis University, he writes a draft of his most famous paper, which he completes at the University of Wisconsin at Madison, the one in which he derives his celebrated inequality. Okay. Important subsequent step, obviously Bell inequality in the version of Bohm, for instance, allows for crucial experimental tests, so we can remember, for instance, aspect experiment and now many other experiments which have proved the same thing, that is to say that quantum mechanics, if you make measurement of correlated system entangled state of a composite system whose constituents are far apart, they prove that there is a violation of Bell inequality. And this is what Abner Shimoni has called an example of experimental metaphysics, because he said before, if somebody would say, but the spin of that particle, is it defined or not, you could not answer, and obviously disproving, showing that Bell inequality is violated, gives an answer to this question. Well, then from the 1980s, Bell writes a series of extremely deep and important papers on foundational matters, which are collected in, apart from two papers. One is the one that Nino was using the transparency yesterday. And now I will pass to mention my personal relation with him, just to stress how I have appreciated him as a scientist and as a man. So we were working in this field, we means Rimini Weber and myself in Trieste, since a certain time. And then when we wrote our paper, we have sent the preprint at the CERN library, not directly to him. And so what really surprised us is that after a few days, we got this, we knew very well his fundamental contribution, and we considered him the greatest scientist in the field of foundation. And so you can imagine our surprise and pleasure after we had sent the preprint to CERN to receive the letters, the following letter. Dear Professor Ghirardi, Rimini, and Weber, I read with great interest and admiration your paper. I see 84-240, so it's the 240 preprint of the year 1984 of the International Center for Theoretical Physics, a model for a unified description of macroscopic and microscopic systems. And this is the paper, and you see that it is IC 84-240, so exactly 30 years ago. Okay. Well, then, after this sentence, we can find Bell, the scientist. So he raises an objection concerning our paper. There is a point in your presentation that makes me fear I have not fully understood you. It is your emphasis on the reduced density matrix rho of Q, because we were working with the statistical operator because we wanted to solve the equation for the statistical operation for a pre-particle of a macroscopic object. So, and to make the calculation, it was much more easy. But in our paper, there was clearly stated that we had in mind individual reduction and not ensemble reduction. However, he says, it seems to me that this only obscures the argument insofar as I have grasped it at all. And the problem is the one of ensemble versus individual reduction. And if you read our preprint, there is a clear statement that we want individual reduction and not ensemble reduction. But then, in order to make the calculation, all the paper is written in the language of the statistical operator. And so it's perfectly right that, well, a typical example is that Philip Peer was convinced that our paper, he did not grasp the fact that we had individual reduction. Was one of the many models giving rise to reduction at the ensemble level. Okay. However, here I want to come back again once more to John Bell, who was absolutely unbelievable as a man. In this letter, you can imagine what this meant for us. Then the concluding sentence of this letter is, of course, I will be happy to receive any reply from you, but I hold the right not to reply to letters to be the most fundamental of human freedoms. This is absolutely typical of John. Okay, then we have the next event that I want to mention is the Schrödinger Centenary Conference at Imperial College in 1987. And before this conference, he wrote to us a letter in which, thank you for your letter of May 20, what you say seems reasonable to me. If you think I have been helpful and say so in a footnote, I will be greatly honored. I send you separately something I have written on this subject based on your work. I wish I could have thought about it longer, but I have to release it now, both because I have to turn to other things in the coming month, and because the deadline for which the paper was promised to the producer of a Schrödinger Centennial book has already passed. I hope one day to discuss with you personally. Well, then he concludes the letter. And well, this is the published paper of the published collection of the paper which were presented at that meeting at the Imperial College in London, which has been edited by Kilmeister. And, well, Physics World, in commenting this, has written at the 90, because John made a very warm and excited talk at discussing the GRW, because essentially it was presented collapse models. So at the 1987 Schrödinger conference, Bell famously championed the GRW theory. Since then and up to his premature end, he advocated Bohm and the GRW and showed a deep interest in them. Well, actually, it has been the first, at this meeting, that I met him personally for the first time, and also there he was exactly John Bell, because at the end of the talk he tells, you should have delivered my talk, because he had described essentially what we have done. Okay, physics. We started immediately discussing the problem of identical particles. That was an open problem in our theory, because the localization, as we have introduced it in the original paper, destroy the symmetry of the wave function for permutation of identical particles. And so we discussed this, and I remember that the discussion was during the official dinner at the meeting, and Rimini and myself discussed this problem, and we wrote, and he wrote, some formula on a paper napkin. In particular, we discussed series reduction, in which the dynamics strives to make objective the number of particles in an appropriate volume. And so you see, you have a factor instead of the factor which depresses one with respect to the other. If you have to state in which the number of particles in this volume, in one of them it is n, in another is n prime, one of the two is suppressed with respect to the other. This S is the number, the occupation number in the volume V, and obviously, since it is written with creation and annihilation operator, automatically satisfies the requirement of symmetry, the symmetry consideration for identical particle, and this suppresses superposition of states which have different number of particles in the volume V. Well, there are three parameters here: the frequency of the collapses, the quantity on which you make the integration, and then this parameter beta, which tells you the rate by which you decouple a state in which you have n particle in that volume or m particle in that volume. So we have three parameters, and we were not very happy about that. But Bell did not pay very much attention to this. So we were worried by the introduction, because he was always calling constant of nature the lambda and alpha of the collapse model. And so we were worried by the introduction of new constant of nature in the model, but John did not care too much. I remember that after a couple of months, I went to Padua. I had been invited there, and he gave the 6 possible words in quantum mechanics in Padua. And when I saw him in Padua, he told me, if you don't write the identical constituent paper, I will write it. Then pure CSL came, which solved the problems in a more compact and elegant way, which is physically equivalent to our original proposal, or a proposal like this. You can prove that if you have a reduction with localization at discrete time, then in an appropriate limit you can approximate as well as you want for all possible times the evolution given by a CSL equation. Okay. Actually, John played a relevant role also in this occasion, because Peer asked him whether he could spend one sabbatical year at CERN interacting with him on his field of interest. And Bell suggested him to come to Trieste and wrote a letter to us concerning this matter. Obviously, we reacted immediately, and Philip spent a reasonably long period in Trieste, 6-7 months, with my support and interacting with me and Renata Grassi. And we were trying to have the relativistic generalization of reduction model. Subsequently, I spent a few months in Pavia, invited and supported by Rimini, who had got a chair there. And this stay of Peer has given rise to a collaboration between us. he grasped the exact meaning of our work and integrating the new idea, that is to say the fact that the preferred basis is the basis of position, fundamentally, he produced the elegant version of collapse model which became known as CSL, and which is a little bit different from what he was trying to do before, mimicking the gambler's ruin game. If you go also mathematically, it has a different structure. Okay. Once more, I consider interesting because it proves how Bell was debated within itself between his role as an accelerator physicist and somebody who liked the foundation of quantum mechanics. So he writes this letter. See, I enclose a copy of a letter of Philip Peer. As you will see, he has a sabbatical year and is considering where to go. He is interested in the problem of quantum mechanics, so CERN would not be a good place. There would be only me to talk to, and most of my time goes on effort more appropriate for this laboratory. He would feel isolated and frustrated here, and this is important. It would be a bit frustrating for me too, for even without anyone to talk to here, I have difficulty keeping away from the quantum question. So, as himself suggests, I pass his letter to you, and he says, I have a very good impression of Philip Peer before your own work. His work on spontaneous wave packet reduction seemed to me the most serious in the literature. And then he gives us the reference of the Peer paper that we know already, obviously. Well, the subsequent important event in which we met has been at the Erice conference organized by Arthur Miller, one of the Zikiki conferences in Erice. And these are pictures here. I will mainly project some picture. Well, this is the picture of the audience. And for instance, you can see Rimini, Beltrametti, David Albert, myself, Miller, the organizer, John Bell, von Weizsäcker, Aspect. I don't remember who is this. Howard, Shimoni, then there is Philip Peer, Greenberg, Daniel Greenberger, and some other people. Probably looking at this picture, some of you.
I should be there.
You were there? Yeah. Oh my God.
I should be there.
At Erice? Yes. Oh yes, you were there. Well, it's difficult there in the back. I did not want to... Oh yes, you were there. I am really getting old. Okay. Well, these are two pictures that my wife took when I was lecturing, and that is Bell listening to my lecture. And my preferred photography is this, that Ennio Gozzi has in his room, in which I am speaking with Bell in August of 1989. Okay. We had further important scientific interaction. One crucial point has been the one of the interpretation of collapse models. John, as it has been mentioned in great detail by Nino yesterday, originally proposed as local beable the space-time point at which localization occurs, what now is reported as the Flesch's interpretation. And the sentence is, these are the mathematical counterpart in the theory to real events at definite places and times in the real world, as distinct from the observable of other formulation of quantum mechanics for which we have no use here. A piece of matter is then a galaxy of such events. This is the Schrödinger Centenary Conference. Then, in Erice, he has given the lecture which is known as Against Measurement, and he claimed the GRW type theory have nothing in their kinematics but the wave function. It gives the density in a multidimensional configuration space of stuff. To account for the narrowness of that stuff in macroscopic dimension, the linear Schrödinger equation has to be modified in this GRW picture by a mathematically prescribed spontaneous collapse mechanism. Well, this is the only point on which I disagreed with John. I am firmly convinced that as many people who are really interested in collapse theory, that they need an interpretation and identification of beables. And limiting everything to wave function in the 3n-dimensional configuration does not lead to a clear picture of the world as we perceive it. So we need an ontology. For this reason, myself, with Grassi and Benatti, my student, proposed what is presently known as the mass density ontology, which at the non-relativistic level represent a meaningful way to make sense of all the implications of the theory. What the theory is about is the mass density distribution in the whole universe at any time. And when we wrote this paper, I sent it to many of my friends, and just to show that there is somebody who adhered immediately to this, I can project you an email by Bas van Frassen. Dear Giancarlo, your message was almost the first I found when I returned here after the holidays, and it makes me very glad. I have talked with my students about your paper and also brought it up in David Albert's seminar, which he was giving here for the fall term. We all agreed that your paper addresses the most important issue about how to relate quantum mechanics to the macroscopic phenomena in a truly fundamental and new way. I will explain below why I see this as a part of a consensus with discussion about other interpretation of quantum mechanics. But there is this difference that you have given in your discussion of appropriate and inappropriate topologies, an important and even to my mind very convincing rationale for this solution. In fact, pages 23 and 24 are my favorite pages in the paper, and this mentioning the topology, I was observing that if I have this table, and I have this table in which one of its atoms, instead of being in the fundamental state, is in an excited state, the two states are orthogonal. So this table with one atom excited is orthogonal, which is the maximal distance that you can have in the topology of the Hilbert space. On the contrary, if you take this table here and without exciting any particle, you displace it of 1 meter, due to the tail, well, they are almost orthogonal, but not completely orthogonal, so the difference is smaller than the one of those. So you cannot use the topology of Hilbert space to distinguish macroscopically different situations, essentially. And this is the pages 23 and 24, fundamentally. Okay, it is interesting to remark that the theory does not tolerate for perceptual times the superposition of states corresponding to different mass density distribution amounting to the different location of a Planck mass in the whole universe. And here I have put some formula. I don't know if you can read it. I use the Fogg representation, and I divide all the universe in cell of 10 to the minus 15 cubic centimeter, because 10 to the minus 5 is our characteristic length. And I use Fogg state, in which I say in the first cell I have M1 particle, M2 particle in the second, plus N1, N2, so these numbers differ. Then the decoupling rate. Then the decoupling rate of these two states, according to spontaneous localization model, is given by e to the minus lambda, the sum over all the particles of the square of the difference of the occupation number of the various cells times t. Now lambda is 10 to the minus 16. If you take for t, so I am playing a game in which also I put our perceptual times, which is of the order of 100 of a second, you get a 10 to the minus 18, which means that since the most unfavorable case is the case in which all these differences are 1 or 0, because if you have a larger difference, the square increases the effect. So in the worst condition, if you have that this sum, which is a sum of 1 and 0, involves 10 to the 18 protons, then this superposition does not persist for the time of our perception. And that is a Planck mass. Obviously, I don't pretend Professor Penrose uses Planck mass in a very different way. Here I have to call into the game also our perception. But however, I think it is interesting to make this remark, which is a feature of our model. Okay, I have discussed either personally or by letter this matter with John several times. Actually, the last letter I got from Bell is this. Dear Giancarlo, well, it was good to see you in Erice. Well, the first thing is that he had, in Erice, asked me to read a paper by Kent in which Kent was trying to make a generalization of collapse model to identical particles. And I proved that the proposal by Kent allowed faster than light signaling. So he writes, it is very interesting that Kent has collided with GRW Theorem. Weierberg also seems to have done so. I hope I will have digested what you say before we meet at the ICTP. But what is very important for me is that he insisted strongly, in spite of the discussions that I had, that as regards psi and the density of stuff, I think it is important that this density is in the 3 n-dimensional configuration space. So I have not thought of relating it to ordinary matter or charge density in 3 space. Even for one particle, I think one would have problem with the latter. So I am inclined, because in my letter I said probably you see that in the 3 n-dimensional space you have the element to have an objective interpretation of the world as we perceive it. And he says, so I am inclined to the view that you mentioned after as it is sufficient for an objective interpretation. And then it comes back again to this point, and it has to be stressed that the stuff is in 3 n-dimensional space or whatever corresponds in field theory. So he had this position at the end of his, this was in October '89, and a few months after he died, unfortunately. Okay, well, for one particle, surely one would have some sort of problem conserving our intuition with one particle, because if you have a mass density distribution of a proton, which takes all this room, but we know very well that the dynamics of GRW is such that if you try to understand where you find the proton in a measurement, and then this is amplified and transformed in some macroscopic change, then the macroscopic change is the one corresponding to having found the proton along the upper path or the lower path in a Stern-Gerlach experiment or something like that. Okay. I must say that I consider a great pity that John did not live enough to deal seriously with this extremely relevant point. I have the impression that nowadays there is an almost universal consensus that the specification what is real is only the wave function is not a satisfactory answer to the epistemological problems connected with collapse models. The last time I met John was at the CTP on the occasion of the celebration for the 25th anniversary of its establishment. All important speakers were Nobel Prizes, but fortunately Abdus Salam was aware of the extreme importance of John's work and invited him to deliver a lecture which was chaired by Alain Aspect. I think this was probably the last public lecture he has delivered, and then it is a wonderful speech by the title First Class and Second Class Difficulties in Quantum Mechanics. There he goes through all fundamental problems of quantum mechanics. He analyzes what he called the second class difficulties, which are the divergences of quantum field theory, and the attempt to overcome them. So he discusses Salam-Weierberg theory and even string theory. Then he passes to what he called the first class difficulties, which are the foundational problem. And he discussed, spent about one half of the lecture discussing collapse model and the difficulty connected with their relativistic generalization. Well, since I heard it, I consider the talk delivered by John as one of the most stimulating of his talk. Accordingly, when some of my friends decided to organize a meeting in my honor for my 70th birthday in 2005, I worked hard to find among the various cassettes that are in the ICTP archive, and I found the video record made of the talk by John Bell. It was an horrible videotape because the camera was standing, and well, but in any case, I got it, and I succeeded in producing a DVD version of it. However, due to the fact that the registration was not perfect, both from the visual and the auditory point of view, and especially for our desire of making the talk accessible to all scientists, Bassi and myself decided to decode, to transcribe it, and to publish it on the special issue of Journal of Physics, the Quantum Universe collecting paper written by prestigious author to celebrate my birthday. And this is the cassette in which there is the DVD, and this is the paper, the Trieste lecture of John Stuart Bell, General Remark by Angelo Bassi and GianCarlo Ghirardi. We comment before presenting the paper. Well, I consider it useful to call attention to this paper talk, as well as to the toward an exact quantum mechanics, which has been used by Nino yesterday systematically, because these are two papers that you don't find in any one of the collection of the paper on foundational problems in quantum mechanics. And well, both of them are quite stimulating and interesting, as all paper by Bell. The second one is the one, and you can find it on Journal of Physics A. The other one is in the books, Themes in Contemporary Physics Second, which is the publication of the proceeding of a meeting in honor of Julian Schwinger, essentially. Okay. The relativistic issue. And this, now we will understand, because yesterday I was thinking that the sentence that Nino has projected was not in a paper. On the contrary, I have checked, and it is in Against Measurement. However, in the Bruno Tuschek lecture, he gave something in which the first lecture was Bruno Tuschek, Quantum Mechanics and Inexact Science. I would like to stress that in this transparency that is stated very clearly, and I like to stress this point, that many times he was telling me, by exact I mean a theory which does not require and is not embarrassed by a conscious observer. Essentially. Well, the second, I have not projected it, the second was devoted to Bohmian mechanics, the second lecture, and so exacted with more parameter, and the third was exacted with nothing but the wave function. And the last transparency of Bell's conclusion, there are too many ways to embedding practical quantum mechanics in an exact theory, but so far we do not know how to do it, or if it can be done with Lorentz invariance. Lorentz invariance is now the big problem, so this is why I was mistaken. Okay. Well, in Are There Quantum Jumps, he had already paid attention to the relativistic problem, as it has been mentioned yesterday. And he says, for myself, I see the GRW model as a very nice illustration of how quantum mechanics to become rational requires only a change which is very small on some measure. And I am particularly struck by the fact that the model is as Lorentz invariant as it could be in the non-relativistic version. It takes away the grounds of my fear that any exact formulation of quantum mechanics must conflict with fundamental Lorentz invariance. This is the first time he spoke of GRW. At Trieste, he considered again the relativistic problem. He was discussing Salam and string theory and this. And after having discussed in detail the collapse model, he distinguished the non-relativistic and the relativistic version. And he says for the non-relativistic version, that is, in my opinion, a very good solution for this problem in the context of non-relativistic quantum mechanics. And if I were teaching non-relativistic quantum mechanics, that is the line that I would take. Instead of all that talk, I would have this new equation, and you would see that big objects have definite configuration, and you would see that little objects like hydrogen atoms are fully represented by the Schrödinger wave function. So this is the situation for non-relativistic. Then there is a world we had already discussed, as I told you, relativistic generalization. There is a whole line of relativistic research here, which has been opened up as the Ghirardi-Rimini-Weber jump. And it remains to be seen whether it will work out well or ill. In any case, there is a program where before Ghirardi, Rimini, and Weber, the field were rather moribund. And then he was perfectly right, because then we had the researchers, for instance, by Roderick Tumulka and the researcher of the group of Bohmian mechanics, about the relativistic generalization of both of Bohmian mechanics and of collapse model. Okay. Important celebration. 1 year after his death, Mary Bell, John Ellis, and Daniele Amati decided to devote a meeting at CERN to honor the memory of this great scientist. Well, this is a picture. I am lecturing in the lecture hall of CERN. Yes, that was my lecture. And in fact, it's the reason for which I have written the list of invited speakers: Professor Penrose, Raukas, Peck, myself, Leinias for the acceleration, Abner Shimoni, Gottfried, Mermin, and Jakiv. These were the speakers of this celebration, the first celebration in CERN. And these are the proceedings of this meeting with the paper that I have, by the author that I have just mentioned, published in 2000 by the Cambridge University Press. Well, now you will allow me to repeat things which are very, very well known, but in a way that I have discussed various times with John, and so I would like to present it just in the way that you will see. Maybe it's not so sophisticated, philosophical, whatever it is, but I think it has some meaning. So the main motivation to do so is that Bell himself has always been fully aware that there have been, and let me state, there still are basic misunderstandings concerning the extremely deep conceptual and philosophical implication of his work, even by part of great physicists. Moreover, besides being aware of it, John was also quite upset by this fact. I can guarantee you that he was really upset. He has expressed this, for instance, in Bergman's Sock and the Nature of Reality, in which he has written, "It is remarkably difficult to get this point across, that determinism is not a presupposition of my analysis, of the analysis. My first paper on this subject started with a summary of the APR argument from locality to deterministic hidden variables, but the commentators have almost universally reported that it begins with deterministic hidden variable, which is not true." And so let me make my very naive presentation of the thing. I will use determinism and realism in a very not refined philosophical way. That is to say, the assumption that when I have two far apart objects and I make a measurement, I get something. The properties that I will get, the outcome, are already there before I make the measurement. This is essentially the form of realism with which I will confront myself. Hidden variables are mathematical entities which either by themselves or in addition to the state vector or whatever you want, just to cover also Bohmian mechanics and other possible theory, determine either the precise outcome of any measurement of any observable, deterministic hidden variable theory, or even only the probabilities of such outcomes, stochastic hidden variable theories. Well, so now I will try to, I insist it's very simplified. However, I will rephrase the argument of Bell. I have discussed it with him. One considers a completely general theory such that the maximal in principle specification of the state of a composite system with far apart entangled constituents determines uniquely the probabilities of all conceivable outcomes of single and correlated measurements. So I have something, when I have specified the state, I know the probabilities. Well, the state is formally specified by two types of variables, mu and lambda, which are respectively accessible and non-accessible. For instance, mu might be in Bohmian mechanics psi and lambda the position of the particle. In quantum mechanics, mu is psi and lambda is not there. And in any other theory, well, in this scheme, I think almost all theories, the Leggett model and the thing, they fall here. Obviously, the inaccessible variables are distributed according to an appropriate non-negative distribution, such that is integral is equal to 1. This is important. I have stressed it yesterday. The two measurement settings are chosen, and the measurement processes are performed and completed, so you have a record in space-like separated regions A and B. The specification of the state given by mu and lambda refers to a space-like surface which does not intersect the common region of the passed light cone from A and B. It screens off one region from the other. And I was discussing this with Bell just when he was writing the novel Cousine, in which he has this picture, and in this picture is stressed we consider a slice of space-time Erlang at the region 1 and 2, and crossing both their backward light cone where they no longer overlap. So that line that he has drawn, just to make clear that there cannot be a space-time point on which you have two causal connections going to A and to B and to B. Okay. The settings can be chosen freely by the experimenter, so there is free will, it is assumed, and the probability coincides with those of quantum mechanics. So from now on, I will not consider quantum mechanics anymore. I have experimental set with macroscopic objects, and I have all the data which are predicted if I use quantum mechanics. Okay. Well, so you take an Napier-Bohm-like situation for a spin singlet with setting A, B, and outcome capital A and capital B, and mu and lambda are the two variables which give the maximal specification. Well, this formula is absolutely stupid. The probability of getting A and B when the settings are A and B and the state is given by mu and lambda is the probability of getting A conditioned by the outcome B times the probability of the outcome B when you have A, B, mu, and lambda. And then you can use what usually is referred as parameter independence and outcome independence. Outcome independence means that the first probability which appears on top does not depend on capital B, and parameter independence means that the probability of getting outcome A for the setting small a does not depend on B once you have specified your state. Well, if you use this, you get B locality, what I will call Bell locality, that is to say the probability of these two joint events, so of getting the outcome, there are macroscopic outcomes, A and B, for setting A and B when I have specified, must factorize in the probability of getting A when I have the setting A and of getting B when I have the setting B. So there is no relation between these two. This is Bell locality. Well, then the game is absolutely trivial because, well, obviously averaging over lambda, which are the variable of which you don't have control, you have to get the quantum expectation value for the considered state. Well, the argument is trivial. The integral of PAA, the same result in the case of a singlet state is 0, which means that PAA mu lambda is equal to 0 almost everywhere. And then, if that is equal to 0, you apply Bell locality, only Bell locality, because that probability is the probability of AA, and that star means it does not matter what I do in B. I can even not make a measurement, times the other probability. But if the first term of this product is equal to 0, then the one in which I have minus A, so if this is 1, this is minus 1, spin up, spin down, it is equal to 1. On the contrary, if it's the second which is 0, then P minus A star A mu lambda is equal to 1. And so, if you make the same game when you have the probability of minus A A mu lambda, so measurement along the same direction, you get 0. And so you show that all the individual probabilities take the value 1 or 0. And since he has assumed that all composite probabilities are the product of individual probabilities, the conclusion is that the probability of getting AB, given the setting AB, mu, and lambda, must be equal 0 to 1, or 1, and this is determinism. So, in this precise sense, determinism is deduced from the perfect Napier quantum correlation and not assumed. And then, well, you know very well the game, you define the difference between equal outcome and different outcome, and you average over the hidden variable, and then you derive trivially the Bell's inequality in the form of Clauser and Orn. And if you want to identify this with the expectation value of sigma 1 dot A, sigma 2 dot B, one easily shows that for appropriate choices of the forward direction and for the singlet state, the considered combination violates the bound and can reach the value 2 square root of 2. Well, the logic of the argument is the following, and on purpose I have written experimental perfect correlation. I don't care about quantum mechanics. I have made this experiment 1 million of times and I have registered the outcome. So the experimental perfect correlation and bilocality implies determinism, as we have seen 1 minute ago. But determinism and bilocality implies Bell's inequality. But the experimental data concerning general correlation, so even when I measured the spin along 2 different directions, implies that Bell inequality is violated. So I have to deny Bell inequality. So from the second of 1, denying Bell inequality means that either I denied determinism or I denied Bell locality. But then, let us take the first horn of the dilemma. I deny determinism. From the first one, I get that not determinism implies not experimental perfect correlation or not Bell locality. And since I want quantum mechanics to be satisfied, this is not a possible choice. And so the conclusion is that natural processes in the sense that they have made before implies that Bell locality is violated. Full stop. Then if one wants, one can add that the particles have already properties before or after, but you can find a lot of statements like Bell's theorem relies on 2 things, the assumption that there are pre-existing value of the variable and the locality assumption. This is totally false. The assumption that there are pre-existing values didn't ever appear in my proof. I have used only B-lock and nothing more. Okay. Well, let us, I don't want to go through some stupid sentences in the literature. Well, and then I will conclude by quoting a last example of the absolutely exceptional humanness of John Bell. During a pause of the meeting at ICTP, we were walking around the campus, actually the Miramare Park, in the Miramare area, and he told me, Giancarlo, you know well how important I consider my interest in foundational problems. However, I must state that I think that to devote oneself exclusively to this kind of study is a luxury. One has also to do something more practical to get paid. This is why at CERN I am so involved in accelerator physics. And at this point my reaction was natural. John, you are putting me in a very delicate position. In the last 20 years I have worked exclusively on foundational problems of quantum mechanics. And his answer was marvelous. Oh no, Giancarlo, you have completely ignored that in this year as a lecturer you have trained an entire generation of young people in teaching them quantum theory. This fact fully justifies your salary, and this is also typical of John. Thanks.